Good afternoon, and thank you for attending today's SBCA webinar, Construction Details for Trusses, Part 2. When metal plate connected wood trusses are being considered for specification in a construction project, there can be questions about if and or how trusses can be used in certain applications. Trusses are highly adaptable structural framing products, but it can be difficult for a building designer to know how a truss can be designed and used to solve a particular framing challenge. To help, SBCA has worked with component manufacturers across the country to gather common truss construction details that they've created and used with clients across the country. SBCA then recreated all of those details in CAD and has made them free for download to building designers through its website, sbcacomponents.com. This presentation is intended for all building designers and is part 2 of this series as we walk through roof truss and floor truss wall assembly details available through that download. And I'll be providing some context and commentary on each one of those designs. This is the 6th in a series of webinars aimed at informing building designers, whether they're architects, engineers, or others in the design community, on aspects of the component manufacturing industry. The goal of this series is to provide structural component design guidance, as well as provide perspective on what today's component manufacturing industry is capable of. And we'll also explore how our industry can be an effective partner with building designers in ways that will make their lives easier and or make them heroes in the eyes of their customers. Now, because the audience for any one of these presentations may include design professionals from different disciplines with varying levels of experience, and who may work from anywhere primarily with single family, multifamily, or light commercial, most of my observations will remain at the 30,000-foot view. My name is Sean Shields. I'm the Director of Marketing for SBCA. I've been with the association for over 20 years now, and will be bringing to bear my experience talking with component manufacturers across the United States throughout this presentation. My goal with this presentation and all subsequent webinars in this series is to share the industry's best practices and to promote the industry's expertise and capabilities. So let's get into it. First, I want to provide a quick summary of what I'm going to cover in this presentation. So I'll start by providing a brief overview of SBCA and its role in the component manufacturing industry. I want to do that because I want to give everyone here a sense of the size and scope of the component manufacturing industry, as well as the role that SBCA plays in that industry. I'll then share a little bit of background on where these construction details came from, as well as some of the roof truss and floor truss basics that are integral to understanding the detail that we're going to discuss today. After I walk through the roof truss basics and the construction details that are focused on roof trusses, I'll walk through some floor truss basics and then walk through the floor assemblies themselves. Finally, I will end with a discussion on how today's component manufacturer can be a valuable resource to building designers in the building design process, and why it behooves them to bring a component manufacturer in as early in the design process as possible. So let's start with SBCA. SBCA is the premier trade association for the structural building components industry in North America. It has over 40 years of history, and over that time, SBCA has developed an extensive network that enables it to reach the entire length and breadth of this unique part of the construction industry. Now, SBCA has a strong tradition of providing sound engineering and fabrication guidance to its members, mostly to help them promote their growth and success in the marketplace. But as that market has matured, its primary focus has shifted to helping build connections between companies and individuals throughout the industry, whether they're in the same local market or spread across the continent. Now, these relationships are typically built through both face-to-face events, virtual events online, and through our various digital communication channels. Our premier face-to-face event is the annual Building Component Manufacturers Conference, or BCMC. These are traditionally held in the fall. We just held our last one in Milwaukee, Wisconsin in October, and our one next year will be in Omaha, Nebraska at the end of September, early October. BCMC brings thousands of manufacturers and suppliers together for a week of intense networking, idea sharing, and business transactions. In addition to the BCMC show, SBCA hosts 3 additional face-to-face meetings throughout the year called Open Quarterly Meetings, or OQMs. These meetings are held across the country and offer anyone a more intimate opportunity to build relationships with some of the largest and most forward-thinking CMs in the industry. Now, finally, SBCA has developed an extensive suite of tools and resources for today's component manufacturer that range from digital quality management software to an extensive library of online training modules. To give you a sense for how large SBCA's membership is, this map is a scatter plot of over 1,300 component manufacturing facilities located in the United States. Of those dots, 907 of them belong to SBCA member companies. As you can clearly see, these facilities reach every community in the country, allowing builders to use the products these facilities put out, whether they be roof trusses, wall panels, floor trusses, and other related building products, no matter where the project is located. To give you a sense of scale, SBCA member facilities sold approximately $9.12 billion in product in 2023, out of an estimated total of $9.31 billion. And last, I just want to say that SBCA is an inclusive organization. We welcome everyone engaged in the light frame construction industry and invite them to get tied into our extensive network of structural component manufacturers and their supply chain. There is an infinite number of opportunities for individuals to get involved, to meet manufacturers, share ideas, solve problems, receive and offer education, and most importantly, build meaningful business relationships that can transform the way anyone approaches their job and will positively alter the trajectory of their business and career. Okay, I want to give you a little bit of background on these CAD structural details that SBCA has created for download before we get into the details themselves. Component manufacturers have been generating details like this for the installation of their products since their inception in the 1950s. With the proliferation of personal computers and software programs like CAD, the production of these details has expanded exponentially over time. In the late 2000s, SBCA embarked on an endeavor to collect the most common details produced by its members and boil them down into a standardized library of details. The idea initially was to encourage component manufacturers to use these standard details so there would be more consistency throughout the country. However, it was quickly recognized that these details would be of great benefit to building designers as well, to help them more easily understand how components could be used to solve various framing challenges. Just looking at how often these CAD details get downloaded, they're one of the most popular items on the SBCA website today. And that's coming from, in 2016, SBCA released sort of an updated version of these details in CAD file formats. And that's what everybody has been accessing on the website today. So I'm going to walk through, again, this is part 2. Part 1, I walked through all the floor truss details. Today, I'll be walking through details pertaining to floor trusses, or to roof trusses, and to some floor truss wall assemblies. Before I get into the details themselves, I want to share a little about the impact of roof truss design and some of the things that impact how those trusses are designed, and just provide a few quick notes on terminology, as you can see on the screen. So a roof truss is designed to span a long distance between bearing supports. And as a consequence, bearing locations, bearing surface area, and contact between the bottom chord of the truss and the bearing surface all play a really important factor in the long-term performance of a truss. Now, roof trusses utilize triangulation, the act of putting cords and web members into either compression or tension in order to span these long distances. To that end, the strength properties and widths of wood used in the construction of a truss, as well as the size of the connector plates, all play a major role in the distance a truss can span. In the roof truss details that I'm going to look at here, we're going to be looking primarily at the heels of the trusses, including trusses with and without overhangs. And in the end, we'll look at a few sort of unique roof truss configurations. So here's detail number 1. This detail brings attention to the need to maximize the bearing area by setting the heel of the bottom chord of the truss flush with the outside edge of the supporting structure, typically a wall. Now, this is particularly important because the top chord in this case has an overhang. A top chord overhang is one way to achieve what would be a typical light frame roof profile, where the roof extends or cantilevers beyond the wall dimensions. Now, with this approach, the overhang introduces bending forces into the heel joint to provide some resistance to that bending, as well as providing a nailing surface for roof soffit material under the overhang. This detail shows how the soffit return should be designed and installed. And as you can see, the bottom of the soffit return should be flush with the bottom of the top chord, and the soffit should run at a 90-degree angle to the wall. Another approach is illustrated in detail 2. So this is trying to achieve the same architectural design with a cantilevered roof truss. In this instance, both the top and bottom chords of the truss extend beyond the support structure of the wall. But instead of a heel joint on the bearing area, an interior joint will be designed to create the load path from the truss to the support structure. So it's very important that the interior joint be centered on the support structure and contact between the bottom chord and the bearing area is maximized. In this case, instead of bending forces being transferred to the heel joint through the top chord, those forces are triangulated between the top chord, bottom chord, and the interior web. Detail 3 is a combination of the two previous details. With the truss top chord and bottom chords extending out over the support structure, there is also an interior joint then that rests upon the support structure. The top chord is extended to create an additional length of overhang, which will need a soffit return to provide resistance to the bending forces in the overhang, as well as create a nailing surface for soffit material. Now, the reason for this approach may be either a desire to have a larger overhang area over, let's say, a walkway, or potentially just from an aesthetic standpoint if there is a particularly tall wall. Again, from a performance standpoint, it's very important the interior joint is centered on the support structure and contact between the bottom chord and the bearing area is maximized. To provide some resistance to the bending forces in the top chord, as well as provide a nailing surface for the roof soffit under the overhang, the soffit return should be designed and installed as shown. Again, just like in the last detail, the bottom of the soffit return should be flush with the bottom of the top chord and run at a 90-degree angle to the wall. Again, most of this from a design perspective is important for load transference, but it also makes installation of all of the sheathing materials easier as well. In detail number 4, we say cases where the designer doesn't want the roof profile to extend over the wall. And sometimes there is a desire to also maintain room for things like bad insulation that can run all the way up against the stub of the truss. There may also be a desire to raise the overall roof height to accommodate mechanicals that are placed in the roof area, maybe just to have a larger storage area or add additional living space. This stub can be designed at the heel to raise the height of the top cord to really any height you'd like. Again, as you see in the detail in the plan view, in the circle at the bottom, you'll want to maximize the bearing area by setting the heel of the bottom cord of the truss flush with the outside edge of the supporting structure. What's not shown in this detail is that when trusses are designed in this way, with this stub raising up the top cord, they're going to want to install some sort of blocking to reduce lateral buckling and rotation forces exerted on the trusses through the roof diaphragm. I think because the stub height can vary widely depending on the desires of the building designer, the method used to resist that lateral buckling and rotation probably vary quite widely. But typically, if you have a stub that's only about this height, as you'd see in the illustration, you would install some sort of blocking in between each one of the trusses. Detail 5 shows the same stub truss, but this time the top cord has an overhang. From a design and installation standpoint, again, you might want to you'll want to maximize the bearing area by setting the heel of the bottom cord of the truss flush with the outside edge of the supporting structure. With the stub, blocking again would typically be required between the trusses. But again, depending on the height of that stub, that blocking may look very different. Unlike the last overhang detail where the bending forces were introduced into the heel joint, here it's introduced into the top cord joint. Again, to provide resistance to that bending, as well as provide a nailing surface for the roof soffit under the overhang, this detail shows how the soffit return should be designed and installed. What should be noted in this detail, which is different from previous details, is that the bottom of the soffit return should be flush with either the bottom of the top cord, or it should be flush with the bottom of the top cord, run at a 90-degree angle, but also run back to the truss, not to the wall. And I think the plan view of this detail makes more sense as you increase that stub height. It'll make it more clear what that soffit return would look like. Moving on from traditional trusses and the heels, we're going to look a little at, in detail 6, we're looking at a bottom bearing flat truss. So this is typically employed when a building designer will want a flat roof design. In this particular detail, addresses bottom cord bearing trusses in this configuration, basically a parallel cord truss. Now, looking at it, it can be easy to think that this truss looks and functions exactly like a floor truss, but that isn't really the case. Going back to part 1, on the left is a detail from SBCA's construction details for CAD. That shows a bottom cord bearing truss, floor truss. And on the right, which is the detail we're focusing on today, detail 6, shows a roof truss. Now, the biggest difference is that the wood members are oriented 2x4 in the roof truss, which is typical for roof truss construction. They're not oriented in the 4x2 orientation that is typical of floor trusses. And that's important to point out just from a structural standpoint. 2x4 puts the wood along its stronger axis. So again, the loads are transferring through the wood members in their stronger axis, or basically the thicker portion of the wood, which allows typically parallel cord trusses, roof trusses that are flat, at the same depth, they're able to span longer distance because, again, the wood is in its stronger axis. Going back to focusing just on this detail, again, from a design and installation standpoint, you'll want to maximize the bearing area by setting the heel of the bottom cord of the truss flush with the outside edge of the supporting structure. just like you would with any other roof truss. But unlike the details of the trusses with the stubs, blocking would typically be required between the bottom chord bearing parallel chord roof trusses. So here's another flat truss, but in this case, it's a top chord bearing flat truss. So this is another approach that a designer can take when they want a flat roof profile. But for various reasons, it may make more sense to do a top chord bearing truss versus a bottom chord bearing truss. Now, again, I want to point out that this, again, looks very similar to a detail that we looked at in part 1 of the SBCA's construction details for CAD presentation. In that, if you look on the right, you'll see detail 3 for the top chord bearing floor truss, versus on the left, you see detail 7 with the top chord bearing roof truss. Again, the major difference here is that the flat truss has the wood oriented 2x4 along the stronger axis versus the floor with the 4x2 orientation. Now, with top chord bearing trusses, the goal is to maximize bearing area for the top chord on the supporting structure. That's key. The bearing surface contact between the support structure and the bottom of the top chord in a top chord bearing truss is incredibly important. To the extent to which, the newest version of the ANSI TPI-1 standard, TPI-1 2022, which governs the truss manufacturing industry, that newest version addresses this for the first time and makes design provisions for lumber defects like wane that may reduce the total surface contact area between the top chord and the support structure. That's how important this is. This detail also shows, but doesn't call out, sort of the maximum of a 1/2 inch gap between the bearing and the first perpendicular web of the truss. As I outlined many times in part 1 of this series, that gap is designed as a construction tolerance and for the potential application of gypsum for fire protection or fire separation. But that gap, that 1/2 inch gap, is an absolute maximum, because when a truss designer is designing a top chord bearing truss, they're checking for several forces: compression perpendicular to grain, bending, shear, rolling shear, and tension perpendicular to grain. And all those checks are dependent on adequate bearing surface contact. And so that's why it's critical to maintain that the expected bending force in that top joint and not exceed that 1/2 inch gap. Typically, if that gap gets larger, those bending forces then increase. For example, a 1 inch gap would double the bending forces going through the joint at the top chord. Depending on conditions, that small change may cause serviceability issues later in the building's life cycle. I'll give you an example. Our technical director, Greg Greenlee, recently inspected a number of buildings where the gap between the supporting wall and the first perpendicular web of the truss was over 3 inches due to walls moving out of plane. And this was creating serious performance issues, including significant deflection in the roof diaphragm. So again, you really want to keep that maximum gap at 1/2 inch. So now this is detail 8. This detail incorporates several elements from past details. Now, sometimes a building designer may desire a flat pitch roof, but they want to add an architectural detail that adds an aesthetic flair to the exterior of the building and or hides mechanicals typically installed on the roof of these types of buildings. One approach is this type of mansard truss. This truss profile introduces an angled pitch at the end of a parallel chord roof truss. Now, important elements of this kind of truss detail include, instead of a heel joint on the bearing area, there is an interior joint that must be centered on the support structure. And again, contact between the bottom chord and the bearing area at that area needs to be maximized. like with the other bottom chord bearing parallel chord trusses, blocking would typically be installed between each of the trusses. Now, in this case, there's also a top chord overhang in the angled portion of the truss. That overhang, again, introduces bending forces into the joint at the bottom chord and tension cords at the top, and tension at the chord of the joint, where the top chord meets the stub. Now, to provide some resistance to that bending, as well as provide a nailing surface to the roof soffit under the overhang, you include a soffit return. The bottom of the soffit return should be flush with the bottom of the top chord, again, like with the other details, and run at a 90-degree angle to the wall. Again, this provides a very interesting design option for building designers. It's actually quite a popular truss design where I'm from in the Midwest. We see a lot of cantilevered mansard trusses for light commercial applications like strip malls and buildings like that. What I think is interesting is that's detail 8. And then you move to detail 9 and you have a regular mansard. I think the reason why that cantilevered mansard detail is included before the regular mansard is, again, because it's more popular for those purposes of hiding mechanicals primarily. But you also create an overhang as well, which is typically good for entrances into buildings. Now, that said, in the regular mansard, the thing to pay attention to is the bottom chord bearing truss still has this angled top chord at the end of it, which as a result creates a typical truss heel instead of a raised heel. This detail again brings attention to the need to maximize the bearing area by setting the heel of the bottom chord of the truss flush with the outside edge of the supporting structure, and to provide some resistance to the bending forces in the top chord introduced by the overhang, as well as provide the nailing surface for the roof soffit. The soffit return should be designed and installed as shown, with the bottom of the soffit return being flush with the bottom of the top chord and running 90 degrees parallel to the wall, or perpendicular to the wall. Okay, so those are the roof truss details included in SBCA's construction details for CAD download. We're going to finish going through that download by talking through a few systems details that involves wall and floor truss configurations. Now, before I get into those, I want to revisit a few points that we covered regarding floor trusses in part 1 of this presentation. So I really just want to share a few observations that impact floor truss designs that come into play in these system details. We're going to be focusing primarily on bearing conditions above and below wall top plates and sill plates. And some of the floor trusses we'll look at in these details will be considered bottom chord bearing trusses. In that configuration, just like the one you see on the screen, the bottom chord typically carries combined tension and bending stresses to the bearing locations underneath the bottom chords. Another floor truss configuration is the top chord bearing floor truss. In that configuration, the top chord of the truss is responsible for transferring forces to the bearings. The top chord then carries the combined tension and bending stresses. Now, typically, floor trusses have webs arranged in a pattern to maximize triangulation of compression and tension forces, which are what allows the trusses to span large distances. There are also perpendicular webs used at bearing locations and at chase openings. Over bearing locations, these perpendicular webs allow for the transfer of forces between bearing walls above the truss and to the bearing locations below. But as we'll note, because those forces aren't typically known by the truss designer, they're not necessarily designed to fully act as the single transference of load between the top wall and the bottom wall. Some of those perpendicular webs also provide chase openings. Now, due to the triangulation that's that's the inherent part of a truss, the depth of the floor truss, as well as the strength properties of the wood used in its construction, play a major role in the distance the truss can span. So today we'll look at a few of the details that cover how to handle bearing walls between two different floor depths as well. Now, in every case, just as with roof trusses, bearing area is crucial for floor trusses because it determines how effectively the truss, one, transfers its load to the supporting wall or beam, two, prevents crushing of the bearing surface itself, and three, ensures the structural integrity of the entire floor and wall and the entire system. So the reason why I point this out is that if the bearing area is too small, the concentrated loads coming through the truss to the bearing location can exceed the capacity of the wall, leading to potential structural failure. We certainly don't want that. A larger bearing area spreads the load from the truss more evenly across the supporting members, reducing stress at the contact point and minimizing the risk of crushing. And we'll see a few details here that seek to do that. The key here is that the truss designer must carefully calculate the required bearing area based on the anticipated loads on the truss and the strength of the supporting wall material. Even the grade and species of the wood used for the bearing surface, both of the truss and the supporting structure, impacts a floor truss's capability and capacity to handle compressive forces. And for these reasons, most of the details that we're going to focus on with the different walls, rough openings, and floor truss configurations should be designed and installed to maximize available bearing area. So with that in mind, let's take a look at the system's details. I just want to make a note as we start off here that the next 5 details will look very similar, but they do have important, if subtle, differences. So we'll start with detail A. And the first thing I want to draw your attention to is that at their end bearing on a wall, these bottom chord trusses will have a band at the top chord. And as I mentioned earlier, in passing regarding bottom chord bearing floor trusses, that band is required at the top chord to reduce lateral buckling and rotation forces exerted on the truss that are transferred down from the roof through the walls to the floor system. In the case of this detail, we're addressing multiple floors where those forces are transferred through the walls, through an upper wall, through the floor to a wall below. Hence, the second thing I want to draw your attention to is for wall trimmers around rough openings, solid blocking needs to be installed in the floor cavity to transfer load between the floors. They may be hard to see, but right now I'm moving my cursor around the blocking that this detail is drawing your attention to, as underneath the trimmers on either side of the rough opening. Now notice in this detail, that solid blocking needs to be installed in the floor cavity, and that blocking is notched to accommodate the banding for these top chord bearing trusses. Now it's important to point out that the blocking needs to be sufficient enough to line up underneath the entire width of the stud pack, including the jack stud, which is carrying half the load transferred through the rough opening header, and the one or more king studs in that stud pack, which are carrying the load from the roof and or floors above. So again, in this particular case, for simplicity, the detail is showing a one jack stud and one king stud with a 2x4 underneath. Certainly, as you added king studs, this might extend it to a 2x6 or a 2x8 in order to provide sufficient blocking. It should go without saying that in order for this blocking to function properly, all the wall trimmers around the rough opening from the floor above need to line up with the studs below for efficient transfer of load. The third thing I want to focus on is that when a truss ends up lined up with a wall trimmer around a rough opening, so if a floor truss ended up in this area, um, blocking will still need to be installed on either side of the truss. Again, this is because the truss will likely not be designed to transfer that load from the upper wall to the lower wall. The truss designer rarely has the information required to know exactly where wall trimmers will line up, and therefore doesn't design any particular floor truss with this loading condition in mind. And as a result, that load will still need to be distributed around the truss and carried by additional blocking in the floor cavity. The final thing I want to point out with this detail is that when a floor truss ends up lined over a rough opening, as you see in this detail right here, the header of the wall below will need to be designed to sufficiently carry and distribute that floor load to the wall trimmers, so to these jack studs. Again, that is not something the truss designer will be responsible for, but as the building designer reviews the truss submittal package, they will need to note instances where this may occur in the building and make sure that this wall header is designed appropriately. In detail B, we see instead of a window rough opening at an exterior wall, we see a door rough opening with either an interior bearing wall or an exterior deck or three-season porch type situation. In this case, when a bottom chord bearing floor truss is utilizing an interior bearing, it's important to maximize the bearing area with full contact along the entire surface of the support structure. The perpendicular webs of the truss panel point, so this area right here, need to be centered over the interior bearing location. And I talk about this in part 1, but as a reminder, the reason why this is important is to ensure both the compression forces at the bottom chord and the tension forces at the top chord are adequately transferred throughout the rest of the truss. Because again, this truss is continuing on to 2 other bearing locations. Again, just like in detail A, solid blocking will need to be installed in the floor cavity to transfer load from the wall trimmers around the rough openings. You'll see them again here and here. Unlike with the end conditions, the blocks will not need to be notched to accommodate the top chord banding, because again, with this being an interior bearing, there is not going to be any top chord banding on these trusses. However, blocking will still need to be installed on either side of a truss if that truss lines up with the jack and king stud packs, and that blocking will need to be installed on either side. Now, in detail C, we see a condition where the rough opening header is, I love this, upset or incorporated into the floor system for an interior load-bearing wall. Now, this can be common for entryways into units from an interior corridor or hallway. Sometimes the building designer may want to move the header up into the floor to accommodate either a taller door or possibly a window above the door or some other design element where they don't want a solid header above the rough opening. In this detail, the header profile is lowered to accommodate top chord bearing trusses bearing on the flush beam header, as you can see sort of in this area right here. Blocking may or may not be added to the bottom of this flush beam header to match the floor depth. So again, you would have blocking on top of the header to accommodate the top chord of the top chord bearing truss. But you may or may not put blocking underneath the header, depending on the depth of the floor and the thickness of the header material that you're using. I will say that there may be a motivation to rest this beam header on the top plate of the wall below instead of installing this blocking. One, for ease of installation, and two, to make sure that you are maximizing bearing area here. But sometimes the depth of the floor may not make that feasible. And so you would add this solid blocking underneath the header. Now, I keep on calling this a flush beam, as it's called out in the detail. And the reason why that is that that header needs to be flush with the outside face of both sides of the wall. Now, in this case, if this header was made out of LVL, which is typically 1 3/4, you need 2 plies to match the width of the 2x4 wall depth. So not a big deal. Potentially another way to do this is with 2 2x6s, sandwiching a layer of OSB. You can typically get to the desired thickness that way. I just want to note too, another way to do this elegantly is to make that header out of a 4x2 parallel cord truss. Well, it could be a 4x2 or it could be 6x2, depending on what the thickness of that bearing wall is. But again, because with the floor truss, the wood members are oriented in the same direction as the top and the bottom sill and top plate of the wall, it's very easy to match that thickness and make that header flush. Finally, I just want to note that in this application, with the use of top cord bearing trusses, it's vital that those trusses are designed and installed to maximize the bearing area. So if you look very closely at this detail right here, you'll see that the top cord bearing trusses are offset. The reason why this is that, again, with these top cord bearing trusses, you're trying to maximize that bearing area and the top cord bearing surface to supporting structure surface area as much as possible. And as a result, when you think about that header material, if it's made out of 2 plies of LVL, if you lined those 2 top cord bearing trusses up, each one would be sitting on just 1 3/4 inch bearing area and on 1 ply, and you basically have forces trying to pull that header apart. So again, not optimal from a design and performance standpoint. So again, the truss designer may typically opt to offset those floor trusses. And while not specifically called out, the other thing that I want to bring in here is you don't see sort of the plan detail, but typically with top cord bearing trusses, we've talked about it a bunch, that there's typically a 1/2 inch gap max tolerance. But in this particular case, with the top cord bearing truss going into a header, and because you're trying to maximize that surface bearing area, that 1/2 inch gap would not be called out. You'd want to have it flush against the header itself. In detail D, we have a condition where the floor truss depths vary. Now, the shallower truss may be possibly a condition for an interior corridor or hallway, and an area where the trusses don't need to span as far as they do in an interior living unit where you'd want to have the trusses deeper. All the same conditions apply as in detail B, and that sufficient blocking will still need to be installed under the jack and king stud packs around the rough openings. So here and here. Again, they need to be sufficient, so they need to match the width or thickness of those stud packs. And again, if you have trusses that line up with those stud packs, you're going to have to install blocking on either side. But what is really different about this detail is that it calls out where and how to install sort of that solid shim material, typically under the bottom wall sill to match the different floor heights. Again, this is calling out one shim, but it may be two, it may be three. It all depends on how much these floor depths differ. One thing I do want to note is that even if you have multiple shims, they do not preclude the need to install blocking under the rough opening stud packs. You still need to install those. This is our last floor truss and wall assembly detail, detail E. And it's very similar to detail D in that you have two different floor truss depths. The only thing that's different is that in this case, both sets of trusses run parallel to the bearing wall. Again, all the same conditions apply as far as transferring load from the Jack King stud pack to the lower wall. But here, there's a little bit of flexibility. The designer could elect to extend the wall studs up into the floor space to match the wall studs of the floor above. But if either for cost or installation ease or whatever, you wanted to maintain standard wall stud lengths, you would need to install a knee wall between the two walls, or between the upper and lower walls in the floor cavity. Now, again, that knee wall would need to include that same blocking. So you'll see the knee wall here, but again, calling out the need to install this blocking under the Jack and King stud packs on either side of the rough openings. And one other detail that I want to point out is that attached to that knee wall, you would also want to install a ledger. That ledger will act as a support for the sheathing installed in the lower profile floor, as well as provide a nailing surface for the edge of that sheathing. Our final detail today is gable end bracing. When the wind blows against the side of a building with a gable end truss, there can potentially be issues because unlike the wall studs directly below the gable end framing, where the studs are oriented along their strong axis, the wider axis, the webs of a gable truss are oriented along their weak axis, or their 4x2 axis. So to provide additional resistance to that wind loading, this detail illustrates how to install lateral bracing to stiffen the gable end members. Now, in this top part, it calls out A, B, and C. And if you look down in section C, you can see that for the shorter gable end members, you can attach bracing to those webs in either a T or L configuration. For the medium length webs, you have section B, so you'd use sort of a U-shaped configuration. And for the longest webs, so an A, this can be a little confusing, but you would attach a diagonal brace that would not go to the top cords of adjacent trusses. You don't want to transfer the load there because the trusses are not designed for that kind of loading. You'd want to attach it to the roof diaphragm or ceiling diaphragm. Well, mostly the roof diaphragm, but if in some cases you can't do that, you can also attach it to the ceiling diaphragm. Again, you want to transfer that load from this diagonal brace up into the diaphragms, not to the trusses, because again, the trusses aren't designed to accommodate that loading condition. And I should note, it's really difficult to provide a prescriptive detail for every condition. And that's why this kind of gable end bracing really is under the scope of work of the building designer. They're the ones who have to specify the specific bracing requirements, because the truss designer, again, is not going to be aware of the forces that are involved at this end of the building. The gable end truss, when we get down to it, is not actually a truss. It doesn't use triangulation the way the other roof trusses do. It's really just an extension of the wall framing. And the building designer is the one who needs to address the potential hinge that's created between the gable and truss and the wall framing. Now, I'll share one quick story about why that's particularly important, is that in scissor truss applications, you have a bottom chord that does not match or would not match the top plate profile of the end wall. And so typically the truss manufacturer will, because they're trying to maintain both the roof diaphragm and the ceiling diaphragm, would provide a gable end truss with the same profile as the scissor trusses, again, to maintain that diaphragm. But that means that you end up with a rather unusual framing condition at the end wall, because again, with a typical like 8 or 9 or 10-foot wall that would have a flat top plate, the scissor truss gable end is going to have a different profile. And so in those particular cases, we have had in our industry over time some significant situations where that hinge has been applied poorly or dealt with poorly. And so SBCA has put out some different details and different guidance with regard to how to frame that end wall to match the profile of the scissor truss. But again, the whole point here is that the building designer really needs to be involved in designing the bracing of that gable and truss, because again, it's really an extension of the wall framing. It's not a truss itself. Okay, so those are the details. With the time remaining, I just want to quickly go through the capacity of today's component manufacturer. This is important because, we talk about scopes of work between the building designer and the truss manufacturer and the truss designer, and it's beneficial for the building designer to know what today's component manufacturer is capable of, and also to know why their products are going to be used on more and more projects going forward. So I want to start out by talking about today's component manufacturer, their manufacturing capabilities. In the last 3 to 5 years, there's been significant investment in the component manufacturing industry. Big part of that is offsite construction didn't become sexy overnight. It's really been sort of a 12-year journey ever since 2012, when the housing market really started to recover and home builders started to feel very comfortable about ramping up production. Again, it's all matters of scale and everything is relative, but it's been very steady. It's been very steady growth over that 12-year period. And that has led to some very significant investments into component manufacturing, because what builders have found out over those 12 years is that they can no longer throw people at the problem of trying to ramp up production capacity. They really need to find more off-site solutions that don't require job site labor. And so because builders have really looked at off-site solutions, one of the most viable solutions, because it's, again, been around since the 1950s, is truss manufacturing. And so there's really been a lot of investment in production equipment, whether it's automated material handling, linear saws, automated jigging systems, laser guided systems, automated nail bridges, even robotics. Everything is moving at a rapid pace towards making component manufacturing more efficient, more accurate, and that results in a more precise and better performing product. And again, looking at this chart on the right, when you see that, when you ask builders, you survey builders, what is their major pain point? It's labor shortages. And where are they feeling the greatest labor shortages? Well, it's with finished and rough carpenters and framing crews. So again, there is a real need for builders to find solutions to make the framing of buildings more efficient than in the past. And some of the other things that are driving um, builders to look at offsite solutions too is even the field labor that they have. They lack the training and skill they traditionally have had. They lack long-term experience, and there's this growing environment of liability and enforcement that's really pushing builders to look at other solutions. And you add to that, builders and developers, as they're trying to ramp up production and lower costs, they're really looking to become more lean on the job site. Um, and they have this motivation to control their costs better, to reduce their construction schedules. They're looking for solutions that are not disruptive to their current processes so that they can easily and quickly incorporate them. And they're looking for something that their field labor can embrace quickly. And so because of that, component manufacturing, whether it's roof trusses, whether it's floor trusses or wall panels, these are all framing methodologies that incorporate well into their current construction methodology and aren't very disruptive to how their labor does things. It just removes a lot of the manual tasks off-site. And again, I think one of the other things that really drives the potential for component manufacturers is, again, looking at this scatter plot of 1,300 manufacturing locations. There really isn't a place in the country where a builder can't get more building components. So it really is, it behooves the builder and the building designer to figure out how they can incorporate more building components into their projects, because it will make them more efficient and help them ramp up production faster. So to conclude, as I hope both parts 1 and part 2 of this presentation highlight, roof and floor trusses are incredibly flexible framing elements. Again, there's been a lot of investment into this industry, and so not only are they flexible, but they're incredibly efficient, they're incredibly accurate, and they can be used in a wide variety of applications to solve many specific design challenges. So whether it's simply changing the depth or configuration of a truss or the strength of the material used in the fabrication, truss designers have many variables at their disposal that they can adjust to design roof and floor trusses to meet a particular need. And hopefully, as these details have illustrated, different roof and floor truss configurations, support structure configurations and locations, and even bearing conditions can be accommodated on any given project. The key is for the building designer to find a way to work with a component manufacturer directly and explore together the wide range of possibilities that exist and find solutions that work best for their next project. I want to thank you for attending today's webinar. Again, I would love your feedback on how we can improve these presentations for building designer audiences in the field. I found that asking questions in the format can be difficult, but my email address is on the screen. I'd more than welcome any follow-up questions you might have. I've had some great conversations over the last few weeks after these webinars, talking about a wide range of topics. If you'd like to talk, provide direct feedback, just shoot me an email and I'll be happy to give you a call. Again, thank you for attending today's webinar. Have a great afternoon.